introduction, and thank you to AI Camp for hosting this webinar. Very cool to see so many people from around the world joining us. I hope that this will be interesting and will be, a useful use of your afternoon, morning, or evening. All right, so let's jump right in. So today we're going to be talking about embeddings, and specifically how to leverage embeddings for use in data curation in the computer vision space. So first off, a quick introduction. So I'm Sam. I'm a solutions engineer currently at Superb AI, where I've been supporting computer vision and machine learning labeling projects and teams for a little while now. So overall today, I'm going to be talking a little bit about the power of data curation. I'm going to be digging into some traditional data curation methods and advantages and disadvantages of these. I'm going to be looking into embeddings and how they can be used in data curation. And then I'm going to be showing you how we at Superb AI envision the use of embeddings and how we currently use embeddings. And then at the end, there'll be time for a Q&A. And feel free to pop any questions into the chat throughout. All right, so let's start with a quick overview of what data curation is and why it's important. So data curation is a pretty critical process that involves organizing, integrating, and enhancing raw data to create a high-quality data set for machine learning models. It's not just about collecting data, but about selecting the right data that is relevant, diverse, and representative of the problem we're trying to solve. In the context of computer vision, data curation tends to involve tasks like data selection, data cleaning, image annotation, and data augmentation. This can be a pretty meticulous process that will require a deep understanding of the data and the problem at hand. But we can't just pay attention to the data. We also need to understand the context in which the data will be used. This includes the problem space, the intended use of the model, and the potential biases that could be introduced during the creation process. So data curation we see as the backbone of pretty much any successful machine learning project. The quality of your data directly impacts the performance of your models. By curating your data, you can ensure that your models are trained on relevant, high-quality data, which is going to lead to more accurate predictions. More specifically, effective data curation can help mitigate common issues like class imbalance and biases in your data set. It's a pretty crucial step that bridges the gap between raw data and actionable insights. But it's not just about improving model performance, it's also about better understanding your models and ensuring that they're fair, ethical, and transparent. By curating your data carefully, you can ensure that your models reflect the diversity and complexity of the real world, leading to more fair and equitable outcomes. So as I've said, data curation plays a pretty direct role in enhancing model performance. When you create your data, you're essentially providing your model with a better learning environment. This is going to include ensuring that your data is diverse and representative, which will help your model generalize better to unseen data. That also involves cleaning your data to remove any noise or errors that could mislead your model. In essence, the better your data curation, the better your model performance. But it's not just about performance. As I said, it's also about trust. By curating your data carefully, you can build trust in your models, ensuring that they make sense to users and stakeholders, and that they can be relied upon to make important decisions. Understanding the relationship between data problems and model performance is key to effective data curation. If your model is struggling with a certain class, it could be due to a lack of representative samples in your data set. In this case, the particular creation workflow would involve identifying and adding more samples of that class. Similarly, if your model is overfitting, it could be due to an overly complex model or a lack of diversity in your training data. Here, the curation workflow might involve augmenting your data or collecting more diverse samples. This process is iterative and is going to require a deep understanding of both the data and the model. It's about finding the right balance between the complexity of the model and the diversity of the data. Okay, let's take a look at some traditional data curation methods and some advantages and issues that they can have. So random sampling is a traditional approach to data curation where a subset of data is selected randomly. In our experience, this is probably one of the most common methods of data curation, probably because it's so simple and easy to implement. But it has its limitations. For instance, it might not capture the full diversity of the dataset, especially in cases where certain classes or features are underrepresented. Also, it doesn't take into account the relevance or quality of the data, which could lead to suboptimal model performance. In the context of large and diverse datasets, random sampling might miss out on important patterns or relationships in the data. This could potentially lead to models that are not robust or that fail to generalize well to unseen data. Metadata-based curation is another traditional approach where data is curated based on its metadata, such as labels or annotations. This approach can be more targeted than random sampling, which allows for more specific and relevant data selection. However, it relies heavily on the quality and completeness of the metadata, which can be a pretty severe limitation. The metadata might not fully capture the diversity of the dataset, especially in cases where it doesn't fully represent all the characteristics of the data. The metadata might be incomplete, inaccurate, or biased, and it might vary in quality across the dataset, particularly when working with data gathered from multiple sources. Often, data scientists and machine learning engineers are working down the pipeline from where data is gathered, and so can be limited in their options to change or improve on metadata. So, while metadata can provide valuable insights for data curation, and it can be a very useful starting point, it's often limited in its efficacy, and we have to look elsewhere for deeper insights about our raw data. So overall, while these traditional data curation methods, while they're effective to some extent, they come with these limitations. First, they often provide an incomplete representation of data. This is because they rely on manual labeling and metadata, which may not capture all the nuances and complexities of the data. Second, the more advanced methods are time-consuming and labor-intensive, requiring significant human effort to curate and label the data. This not only slows down the process, but also increases the risk of human error and bias. Third, more sophisticated traditional methods struggle with handling large data sets. As the volume of data grows, it becomes increasingly challenging to manage and curate the data effectively. And lastly, these methods can have limited scalability and adaptability. They're not designed to evolve with changing specific data needs and trends, making it difficult to keep up with the rapid pace of advancements in the field of computer vision. Okay, so let's talk about embeddings. Embeddings are an extremely powerful tool in machine learning and computer vision. Essentially, they're a form of feature extraction or feature learning, where raw input data, such as images or natural language, gets converted into a lower dimensional continuous vector representation. These vector representations, or embeddings, encapsulate relationships and patterns in the data, making it easier for machine learning algorithms to make accurate predictions or classifications. Embeddings can offer several benefits, particularly in the case of unstructured data, such as raw, unlabeled images. They let us handle large data sets more efficiently, improve model performance, and gain deeper insight into the underlying structure of the data. There are various types of embeddings, including those created using convolutional neural networks, or CNNs, autoencoders, and pre-trained networks. Embeddings have a wide range of use cases, from image generation and style transfer to data organization. So let's think a little more specifically about how embeddings can be useful in the computer vision space. One of the cooler things we can do with embeddings generated from visual data is to make a potentially vast amount of unstructured, unlabeled images searchable by, say, visual similarity. So how do we do this? Well, we can transform each image into a vector, as discussed, using, say, a convolutional neural network. And then we can use a k-nearest neighbors algorithm to find the images that are closest to the given image in the vector space. Depending on the techniques we're using, embeddings can capture similarity at the image level, such as palette, lighting, or time of day, but also at the level of more granular features, such as the presence of specific objects. We'll talk a little later about some of the techniques that that we at Superb use, but there's a huge range of ways in which we can capture information about images and embeddings. And the uses of this sort of vector space analysis can be vast. We can use them for specific image retrieval, for recommendation systems, for photo managers, and much more. So there are a number of ways to generate embeddings. As I mentioned, one popular approach is to use fancy deep learning models like convolutional neural networks, as mentioned, or autoencoders. And these models are trained to figure out a compact, lower dimensional version of the input data. Another good method is to take advantage of pre-trained networks and transfer learning. These pre-trained networks have already been trained on big data sets and have learned how to extract useful features from the data. We can use these learned features for our own tasks, which is called transfer learning. Once we have our embeddings, we can make them visual by using techniques like t-SNE or PCA to reduce the dimensions and potentially display the embeddings in a two-dimensional space, something easily parsable by the human eye. So here we see an example of this sort of 2D visualization. And this is from within the Superb AI Curate platform. And it's using the fashion MNIST dataset, which I'll show you more of later. As you can see, this already starts to give us some interesting information about the general visual structure and contents of our dataset. And it lets us pick out sets of visually similar or distinct images. We can see long sleeve and short sleeve t-shirts are selected here. And then we can see a huge swathe of shoes that have been identified as visually similar by the embeddings algorithm down here, running from high-heeled to clogs to sneakers up here. Now, once these embeddings have been generated, we're not done. It's critically important to check and improve our embeddings. We can do this by seeing how well they perform on certain tasks or by fine-tuning them with our own data. Finally, as I've mentioned, these embeddings have practical uses in image retrieval and recommendation systems, but critically, they can be used to take data curation and organization to the next level. All right, so let's dive into Superb Curate, which is our tool using embeddings. It's designed to revolutionize the process of data curation in computer vision. All right, so let's just quickly talk a little bit about how we use embeddings. When images are brought into the Superb Curate platform, we generate embeddings for each of these images that have been uploaded. In this case, we're generating a 1024 dimensional vector to represent each image using a combination of embedding algorithms. I'll talk a little more about which embedding algorithms we use later. We can collapse this vector from 1024 dimensions, as I've shown, down to 2 dimensions, so we can easily visualize it. So just looking at this, we can start to see trends in this data. We can start to see clusters of visual similarity, images that are relatively distinct from the rest of the data set, and so on. We talked about searching your data by similarity, and here we see how we might do this at scale. If we want to pull out a really specific type of data for labeling and training, we can really easily select a subset of this data and add it to a slice. I'll talk a little bit more about generating and modifying slices of data shortly. But for now, this is a really powerful way to quickly extract meaningful subsets of your data without relying on metadata or human labeling. So this is a really straightforward and powerful way to manually use embeddings to understand more about your data and to select or build out similar subsets of data. But when we talk about selecting subsets of data, there's the broader question to be asked, the one that's fundamental to every model training pipeline. Almost everyone working to create labeled data in the computer vision space has more data than they can immediately label. And as such, we have to select a subset of that data to label first. Like even if we're planning on labeling all collected data, selecting that first subset and subsequent subsets is critical to an effective and efficient labeling workflow. At Superb, we think one of the best ways to label large quantities of data is with an iterative active learning model. First labeling a small subset, training a labeling model, using that labeling model to generate initial labels for the next subset, correcting these automatic labels, training a new model, and so on. And so having the most effective model as soon as possible can slash your total labeling times. All right, so for this example, let's take a look at a slightly larger data set. So this is the MNIST handwriting data set. Here we can see the overall clustering of this data set. But here we have about 70,000 images, all unlabeled currently. So let's pick out an initial subset to send to our labeling team. So it's pretty much as simple as selecting auto curate, selecting what to label here. In this case, we're only working with unlabeled data. And then picking an initial subset to label. Let's pick, say, 20,000 images. And we pick the name of the slice to add it to. Okay, so this is going to take a few minutes to run. So let's take a look at some curations that I've run earlier. So here is a report from one of these curations. Every auto curate process that we run will create first one or more slices of data, which we can then review, slice further, add to, or send back over to the label portion of our suite for our labelers to work on. We can review all these slices in the Slices tab here, or just directly via the curation history, just by clicking on these slices. But equally importantly, each of these processes will create a report, which lets us see how this embedding-based algorithmic data creation process will work, or is actually working. So we see this type of reporting as really critically important to any data creation process. We need to be able to understand exactly how and why these subsets are being curated so that our models are transparent, but also ethical. So starting at the high level, for the purpose of this report, we always compare our curated subsets with a randomly selected subset of the same size. So this is the core of the process. In that 1,024 dimensional embedding space that we mentioned, we group these images into clusters of varying sizes. So we can say that these clusters are images that are semantically similar to each other. It's likely that within a cluster, images will have similar utility when it comes to training a model. Some of these clusters are quite large. So this would be a set of images that are relatively similar looking, and it might be better to select less from these large groups. Sparse clusters, on the other hand, might only have a few images in them. And these images don't look a lot like other images in the data set, and as such could be considered edge cases. These can be crucial for model training, and it's important to make sure that they're well represented. So in our report here, we can see that the algorithm has grouped the data into almost 15,000 distinct clusters. A random sampling has only selected data from about 2/3 of these clusters, while our curation has selected data from 100%. But moving on in the report, we can really start to see the way in which our auto-curate algorithm pulls ahead of a random sampling. With larger clusters, we can see it's pretty probable that a random sampling will select some images from the cluster. But with smaller clusters, that becomes increasingly unlikely. For clusters of size 1, so that's just an individual image that doesn't look like other images in the data set, about 2/3 of these images have not been sampled by the random sampling. For clusters between 2 and 5 in size, almost 1/3 are missing. Including these high-value, semantically distinct images in an initial data set to label is critical to get a model off the ground as soon as possible. Okay, so let's take a look at some more concrete examples in the report. Our reports will provide examples of what it's identified as sparse and dense clusters. So we can pretty much immediately see that more well-articulated characters with heavier lines seem to be well represented in this data set and might be over-selected from in a random sampling. Whereas these messier images with disrupted lines or more noise or fragmentary dots are probably edge cases that should definitely be prioritized in our initial labeling and training data set. So embeddings aren't only useful when dealing with unlabeled raw data. Far from it. By generating embeddings for labeled data at the object level, and then clustering the objects, we can do a number of interesting things. We can QA our labels. We can look at the semantic distribution of the objects. And we can even use the same principles that we use to curate data to initially label to curate a subset of labeled data for testing. So let's just move over to a data set with labeled data here. So let's first talk about the last option here in our auto curate options, which is QAing our labels. High quality data is essential to develop accurate models, but QAing is time consuming and random QA checks are likely to miss issues. We can use embeddings and embedding clustering to make educated guesses at which labels might be mislabeled. Basically, we can look at individual objects that share a cluster with different object classes, but not with any labels of their own object class, or with very few labels of their own object class, and mark this label as possibly incorrect. By putting together a list of these labels, we can focus our QA on labels that have a high likelihood of being incorrect, as opposed to a purely random review, making better use of our valuable QA time. So we can run this mislabel curation here, basically the same way as we ran the previous one. So let's take a look at this mislabel detection report that I ran earlier. So first we can see a breakdown of possible mislabels by class compared to the full data set. And then we can, at the end, we'll take a look at some examples of this data set, examples of the mislabels. So these labels are from the LVIS data set, which is a public, high quality QA data set. So we shouldn't expect to see too many mislabels here. We can see that there are too many actual mislabels here. So we can see that there's a number of possible mislabels for the banana class, books, carrots. These are our highest likelihood. These are classes that we've identified as being the highest likelihood of being mislabeled. And so we can see graphical representation of these relative to the overall data set. We can see that carrots, apples, and oranges are all relative to their representation of the overall data set, more likely to be mislabeled. But let's take a look at some examples of what our algorithm is identifying as possible mislabels. So as I mentioned, it's unlikely that there's going to be too many actual mislabels in this data set, but there are a few interesting things we've picked out here. Most of these look like obscured or unusual instances of a banana, but we can see a couple of actual likely mislabels. So this one here and this one here both look like mislabels. But we can also see a few that raise some interesting questions, like this clearly plastic banana, the banana phone here, and this giant plushy banana. So while under some guidelines, these might constitute correct bananas, these also might be mislabels and might require an update to our labeling guidelines or some fine tuning. So once the data is QA'd and mislabeled, and we've detected and reviewed mislabels, the next step in the pipeline is going to be model training and testing. Generally, the labeled data is divided into a training and a smaller testing set. This testing set is often randomly selected, but as we've considered with unlabeled data, a random sampling can fail to represent sparse object clusters and edge cases, which can lead to possibly skewed validation and testing results. So in this instance, we can use our object level embeddings and clusterings to curate a validation subset that prioritizes both balance at the class and embedding level and is semantically diverse. So if we go ahead and run an auto curate for the split and train validation set, we can pick our validation and training set breakdown, and then we will name our slices. We can kick this off. So I'm going to take a look at a report that I ran earlier for the training and validation subsets. So this one's going to be pretty information dense, so I won't spend too much time looking at these tables here. But basically, we provide a breakdown per class of the different object counts and distributions between the curated validation set, the training set, and any mislabels detected, which we automatically run as part of this process. In these graphs, we can see some objects with more variable clusters, such as bananas, are going to show up relatively more in our validation subset to make sure that we have all clusters accounted for accurate training. And down at the end, we can see an example of our sparse cluster and dense cluster examples, detected mislabels, but also, these edge cases here. So let's talk about edge cases again in a little more detail. We've already talked about, like I said, we've already talked about mislabels, but let's dig into these edge cases. So while we can see edge cases as part of these other reports as an overview of these sparse cluster examples, in the context of creating what to label or the model training curation, of course, it's often useful to specifically pull out these edge cases on either the image or the object level. This is something that many people we've worked with have specifically requested. We can use this information when we're identifying object instances we might need to expand on in our data set, when we're QAing our labels, or when we're trying to just better understand our models. We can generate these edge cases via the auto curate option here too. And we can find edge case objects at the image level or at the object level. But in this case, we'll look at it in the object level. So I'm going to also here just pull up a report that I've run earlier, because this will take another few minutes. So we can see first here a breakdown of the edge case count per class. Some of these classes pretty clearly immediately have more sparse or solo clusters, which means it's likely that a model might have a harder time handling these. Scrolling down to the graphical representation, as we noted before, we can see that the fruit here are a pretty standout, whereas people and cars are significantly more homogeneous. This confirms the creative validation set we saw earlier. If we want to accurately measure the performance of our model on bananas, say, we might need to pick a larger and more diverse set of bananas to test it on. Down here at the after these graphs, we can see some examples of created edge cases. So we can see here that our banana phone has showed up again, but we can also see a significant number of sliced bananas. So this might be a category that we'll need to focus on if we want to improve model performance. Scrolling down to books, we can see a high proportion of partially obscured books, which is probably expected. But we also see a number of magazines. This might be something we need to pay attention to. Further, for carrots, we see a significant number of sliced carrots or pieces or thin pieces of carrots. This could actually prompt us to reconsider our class definitions or just dig further into the incidences and utility of detecting these sources of unusual distinct edge cases. So basically, this sort of report helps us better understand and also improve our data sets and our models. All right. So let's pull back to our demo here. So at a very high level, we're leveraging advanced machine learning algorithms and the power of embeddings to efficiently manage and curate data. This is going to lead to improved model performance, more accurate and effective computer vision systems. So as I've shown, the key features of our platform are auto curation, efficient handling of edge cases and mislabels, and advanced querying and slicing capabilities. We see these features as a way to leverage embeddings to address the challenges of data curation, making the process more efficient and less prone to errors. Our vision is to revolutionize the field of computer vision through more efficient and effective data curation, and our mission is to provide a tool that makes this process as seamless as possible. So, as you've seen, the suite is packed with unique features designed to enhance the process of data curation. Our auto curation tool uses advanced algorithms to identify and curate relative data based on predefined criteria. This saves time, but also ensures that the created data is of high quality and is relevant to the task at hand. We have mechanisms that use embeddings to handle edge cases and mislabels, ensuring the quality and accuracy of your data. Our querying and slicing capabilities allow for efficient data retrieval and segmentation, while we have also these advanced reporting and analytics view to provide insights into your data and provide increased transparency in model training. And so we integrate powerful models and sampling algorithms to ensure optimal performance. And these models and algorithms are constantly updated to incorporate the latest advancements in machine learning, ensuring that Superb Curate remains at the forefront of data curation technology. So let's take a look at the tech behind Superb Curate. So models and sampling algorithms form the backbone of Superb Curate, driving its ability to curate data effectively. So models play a crucial role in understanding and analyzing the data in question. Our embedding generation process specifically uses Dino, Clip, and Bet together. At a high level, Dino is particularly effective at preserving fine-grained details and generalization. Clip, as an image text prediction model, is useful for capturing abstract expressions and color information that would show up in text captions. Whereas Bet is suitable for handling high-resolution images and is very robust at dealing with adversarial attacks. So in this case, it means it can capture objects' high-level semantic information, even if there's occlusion or truncation. And we combine these models together to be able to represent both high, low, and object level information about the image. And so along with these algorithms, our sampling algorithms ensure that the data created is fully representative of the entire data set. And I've discussed a little bit about how these work. So together, these models and algorithms enable Superb Curate to deliver high quality, relevant data for model training and validation. The integration of these components has a significant impact on data curation, leading to improved model performance and more accurate results. Looking ahead, we plan to continue enhancing our models and sampling algorithms, incorporating the latest advancements in machine learning to further improve the capabilities of Superb Curate. We are also exploring the integration of reinforcement learning for embeddings and the development of multimodal, interpretable, and real-time embeddings. So why pick Superb Curate? First, I think we offer a wide variety of curation options to meet possible user needs. Working in the computer vision space, I regularly see machine learning engineers and data scientists encounter a diverse set of pain points, selecting an initial set of images to label, selecting validation sets for testing, identifying edge cases and strengthening model performance on them, and ensuring data quality by finding mislabeled images. As you've seen, Superb Curate is designed to meet these diverse needs, offering a range of options that can be tailored to the specific requirements of the user. For instance, we can curate what to label from initially collected raw images. We can curate what to label with pre-annotations. We can curate and split label data into training and validation sets, create edge case images or objects, pull similar images from a scatter view, or drill down and detect mislabels. We think this end-to-end holistic view of data curation using the power of embeddings produces significant cumulative effects on workflow efficiency and model performance. Looking ahead, we plan to continue enhancing our user-centric curation capabilities, incorporating user feedback and the latest advancements in machine learning to further improve the capabilities of Superb Curate. On that note, we'd love to hear your thoughts about what sort of curation problems and pain points you're encountering. So let's take a look at some concrete results from our testing. We've put together a series of experimental studies to evaluate the performance of Superb Curate using key performance metrics such as accuracy, precision, recall, and F1 score. So all pretty standard. Our results from testing on datasets like MNIST, which I've shown you, MS COCO and LOCO, demonstrate the effectiveness of Superb Curate in curating data and improving model performance. Working with the MS COCO dataset, we used our auto curate in the same way that I've shown you earlier to select a subset of unlabeled data to start with. When we train models on a curated 25% subset of data, and then compared it to models trained on the complete MS COCO training dataset, we saw only a tiny reduction in performance, with less than a 0.05 change in the F1 score across almost all object classes. This result speaks for itself. Using this sort of data curation, we can jumpstart model development with only a fraction of the labeling time. Also, in our experiments on the LOCO dataset, by utilizing our auto-curate features to carefully select which data to include in the validation set, we saw a remarkable 14.5 increase in F1 score on average across all object classes relative to a random sampling. I think these results provide pretty valuable insights into the capabilities of Superb Curate, and they'll inform our future work. We plan to continue building on these results and conducting further experimental studies to evaluate and enhance the performance of Superb Curate. So overall, Superb Curate offers a range of benefits and advantages that make it a valuable tool for data curation and computer vision, and show how embeddings can be used to powerfully improve computer vision workflows. It helps improve model performance by curating high quality relevant data. We can also enable efficient data management, reducing manual effort and saving time. We can handle large volumes of data, making it suitable for projects with massive data ingress. And its user-centric approach to data curation ensures that it meets the diverse needs of users. One of the core value propositions of Superb Curate is its ability to use fewer data to achieve similar or better model performance. So what are the takeaways? I think we've looked at the critical importance of data curation in computer vision and the possible role of embeddings in this process. We looked a bit at the technology and techniques that are used in generating embeddings. We introduced Superb Curate, which is a powerful tool designed to streamline data curation, and discussed its unique features and benefits, and how it uses embeddings to achieve these. We also shared the results of our experimental studies, demonstrating the effectiveness of Superb Curate along with embeddings in improving model performance. Looking forward, we're pretty excited about the potential of Curate and embeddings in general to empower the field of computer vision through efficient data curation. And of course, we're committed to continuously enhancing its capabilities, incorporating user feedback and the latest examples in machine learning to make data curation as seamless as possible. All right, thank you so much for your time today. And we're looking forward to answering any questions you might have.
Right, great. Thanks, Samuel, for the great presentation. And I see we have quite a few questions in the chat. Tyler is answering them. Again, if you have questions, you can keep a post in the chat, or if you prefer to speak to ask questions, open discussion, follow up, make comments, feel free to raise your hand and I can unmute you. And meanwhile, maybe do you think you can see some questions in the chat is either not answered yet or was to talk a little bit more on that?
Let me take a quick look here. So it looks, so you're asking, so one question I saw that wasn't asked is how are 2 dimensions chosen from the 1024 other dimensions? So we're not just picking 2, we're reducing the 1024. And in this case, we can use a number of techniques like t-SNE or PCA. I think we use a variety of t-SNE, although that's somewhat our secret sauce. Looks like I think Tyler has answered pretty much all of the other questions in the chat there that I can see. Thank you, Tyler.
I see a new one is coming. It's from Daniel.
Yeah, that's a great question. And that's certainly something we can look into moving forward. I think there's advantages and disadvantages to working in 3 dimensions. 3 dimensions can be harder to parse visually. Working in VR is obviously very powerful, but also can be inaccessible for a lot of users. So there's certainly pros and cons. I think 2 dimensions is probably one of those maybe a sweet spot for easy accessibility and preserving information about the semantic space. Using color is also a good idea.
I think a question from Kimberly asking how many people working on the super AI.
I don't have an exact number, but we have a pretty decently sized dev team. We have dozens of machine learning engineers working on this technology. Okay. From San Huang, could you explain the edge detection more? I take it you're talking about the edge case detection. So when we talk about the so as I've shown in the as I showed in that 2D representation, basically we're clustering images into groups based upon how close they are, how closely semantically related they are to other images. Edge cases are images that are not similar to any other images, so that they are in a group of one or a group of just a few.
By the way, I enable the unmute yourself the abilities. So, if you want to speak to us questions or discussions, you can just feel free to unmute yourself. I think it's if it's more convenient. Thanks, Wayne, for sharing your feedback. Yeah, I hope to can learn some things from the today's topic for your computer vision project. It's great.
I see from David Menkins, he says that there was some work done using motion as another dimension, which groups objects with the same movement to stand out, and they can be separated by different motion types. I think that's a really interesting work, and I think it's definitely representing these complex vector spaces is definitely an ongoing problem. The best way to handle this. I think there's a lot of different ways we can approach that, and it's certainly not a solved problem. It's the best way to handle this, and the most robust way to handle this.
Hey, Sam. There is a great question from Gearing. You see it? Great presentation. I see a lot of teams working on similar technologies, Anchor, Landing Lens. Is there any USP of Super BI you want to comment on? What is USP? Value proposition difference?
Yeah, so I think that one of our unique, I think one of our unique selling points is our combination of the combination of embedding algorithms we use, and the specific combination of this that we've demonstrated it to be highly effective. I know some competitors might only use one embedding, one of the above embedding algorithms, like CLIP. We use a combination of three, and we combine them in a way that preserves information from each of them. And our experimental results, I think, have been very effective.
Thank you.
So a really interesting question is will concentrating edge cases deteriorate the performance for the majority, from Dimbo. And so that's a really challenging question, and it's something we're definitely considering. In some cases, when the number of edge cases is extremely small and they are too specific and very semantically distinct, or not, and they are unlikely to be found in the real production environment, including them in the model validation or training can actually result in degradation. So it might be worth removing those from the data set. Another question, did we try edge detection on stereo imaging? Not currently, I'm afraid.
We have a couple of minutes to go. Any last minute questions? Again, feel free to raise your hand or unmute yourself if you want to speak to ask questions or make comments. If it's easier. One question is, have you tried the video cases?
That's a good question. We've done a little bit of experiment with video cases. I would say that both sorts of curation work most effectively when we have a diverse data set that we need to select a subset from. If we're working with video frames, there tends to be a lot of semantic similarity between video frames, which can result in which can make the algorithm a bit less effective. But this is also something that we're experimenting on, and equally we're quite curious if this sort of technique can be used to extract the most significant frames from a video, or frames with specific objects present. So this is definitely something that we're continuing to work on, although most of our experimentation up until now has been on image datasets.
Someone is asking for the homework. That's great. Yeah, I think there's some great way to learn, and I'm not sure if there are any Jupyter notebooks or code labs.
Yeah, if you want to reach out, we can certainly, if you're interested in like a demo of the suite's tools, and you're interested in using the suite Curate, we can get you set up with our suite if you're interested in that. And the suite, both the Curate has an SDK.
Maybe the last question from Daniel. He's asking about the concentration on the edge cases.
So in this case, it sounds like you're looking on, it sounds like so the question is there a measure of edge case saturation to determine if the analysis of edge cases will drift the central population? So we're talking about basically analyzing the performance of the model based on the inclusion of edge cases. That is a very interesting question. And in essence, we're talking about diagnosing issues with models here. And that's not something that's currently a part of Superb Curate, but it is something that we are working on as a suite, an independent part of the suite to diagnose model performance, which yeah, I think I think that's a really interesting and critical question.